For those of you who don't know me, I'm Steve Beckwith. I'm from the University of California. I'm not scheduled to give a speech, and I won't actually give one, but I did want to just make a couple of remarks because Keck has been so important for UC, such a great asset. And so first I wanted to thank everybody here for the opportunity to be part of this. This is just a phenomenal celebration. And to mention that at least on the UC side, the Keck has been a remarkable tool both to forward the university's mission, to recruit some of the most talented people on the planet, and frankly to become very close partners with Caltech, one of the other great universities within the state of California. I have noted that Keck has produced for UC as well as for Caltech and others a number of prizes, certainly many discoveries. That's part of what we do as a university. And as terms of being innovative, I also have to note, I don't think everybody here has noted yet, that the Keck architecture is being adopted by almost everybody else, including in the space business. If you look at the James Webb Space Telescope, it consists of hexagons, and it folds up, and it has little actuators behind it. So I think the dream that started with Jerry Nelson and others back in the 80s has really taken hold and has created a future for these large telescopes, both on the ground and in space, which is very important. My own take in looking at some of the talks this morning and also in looking at the science is that the Keck itself does still have a very bright future. I know there's a lot of talk where UC and Caltech are involved in another partnership to build the next generation. But if you just look at the possibilities still to come with Keck, with the adaptive optics and new instrumentation, and just using up the focal plane, since usually we build telescopes and we only capture a few percent of the photons that we actually manage to image in the focal plane. There's a lot that's still to be done. And so I'm really very pleased that UC is part of this partnership, and I want to say on behalf of the university, we look forward to working with our partners, with Caltech, of course with the new partners on the big projects, and also the University of Hawaii, NASA, and the NSF. It's really been a great run, and it's not over yet. So with that, I would like to introduce our first speaker in the afternoon, Mike Mumma, who is going to tell us about observing the solar system with Keck. Mike?
Thanks, Steve, very much. I want to thank particularly Taft, Armendroff, and for inviting me to come and speak with you today. And also, especially all of the support astronomers, the staff, and so forth of the Keck Observatory who have assisted me and so many other of the astronomers in this room in pursuing our science over the last 2 decades. It's been a wonderful experience, and we intend to have it continue for quite a long time to come. I'm going to actually be talking mainly to the non-astronomers in the audience because you are all people who were achievers in your earlier careers, maybe your present careers, and you're here because you're really interested in understanding what we're learning about the world around us, about the solar system, and beyond. So I'm trying to reach you, and so the astronomers, the pros, can decide whether to listen or not, but I particularly would like to try to have a conversation with the other folks. So I will start with the question that every human, since man has crawled out of trees, thinks about, namely, why are we here? Why is Earth wet and alive? This is not a trivial question. The nature of the Earth, the very presence of life on it, depends on a whole sequence of events going back to the Big Bang. The Big Bang, just to remind you with this cartoon, created the first 3 elements. That's not the laser pointer. Okay, they created hydrogen, helium, and lithium. Over the next 10 billion years, 9.5 or so, successive generations of stars then made those into heavier elements. The first generation of stars made elements up through iron, which were sufficient to make iron-rich bodies, but not sufficient to make life as we know it here. And later generations then processed heavier elements through supernova explosion and so on. And the last 4.5 billion years have actually been the period of particular interest for understanding how our planetary system came to be, and indeed how life itself came to be. So let's just review the cosmic cycle of matter, as we call it. Essentially, matter is ejected from stars. Essentially, they lose that mass to the interstellar medium. Here you can see a ring of material around this particular star. That material later is exposed to light in the diffuse medium, then recondenses and reaccumulates into clouds, where it forms new young planetary systems, such as our own, and then on to the evolved planet and star phase, which we're in right now. And ultimately, the star-planet system dies, and the cycle begins anew. The star-forming region will be addressed in detail by Jeff Blake in his talk, but just remind you, this is actually a Spitzer infrared image of the star-forming region called the Mountains of Creation in W5, and those bright spots of light, indicated by the arrows here, are actually places where young stars and planetary systems are now forming. And indeed, when you look at one of these systems edge on, you see a disk of material. And when it's edge on, it looks flared because the material farther from the star is raised farther above the midplane of the disk. And so what we care about with respect to that disk is what are the processes that occurred on material there that might later be carried into future planets, into future bodies that would impact on planets, and so on. And for those on the other side, I want to show you that I can actually point my laser to the left as well. Okay, so that's where we're going, and I don't intend to talk about the details of these words, but this will all be online someday, and you folks can have a look at it in detail if you wish. Okay, so where do we get clues about what happened in our protoplanetary disk? Well, there are 4 talks in this meeting which deal with that. Jeff Blake's will talk about disks themselves. You'll hear from Jeff Marcy on exoplanets and so on. And then Mike Brown just gave a stellar talk about the distant solar system beyond the planet Neptune. So I will confine my remarks to things within that. And of course, you heard this morning from the AO specialists about the exciting work going on there through imaging of planetary bodies in the outer solar system as well. So I will talk primarily about the major planets and small bodies. In particular, I'll first examine what we've learned in 20 years, where are the frontiers in the coming decade, and especially what role does, and will the Keck Observatory play in all of this. So let's look at 20 years ago, not very long ago. What was our solar system like? We had 9 major planets, right? Their larger moons were known and an asteroid belt. And of course, the Voyager system had flown through the outer solar system, so we knew quite a bit about that and other things from space missions. We knew that a comet reservoir should exist beyond Neptune. Now, you've seen in Mike Brown's talk a beautiful example of the trans-Neptunian objects and how their orbits have been defined and so on. But its first member was discovered only in 1992 and published in 93, so it's within that 20-year remembrance time for Keck. Beyond that, at very distant, almost halfway to the nearest stars, there is another distant comet reservoir, which is called the Oort cloud, and 20 years ago, people knew that had to exist, and the theory was that those comets had been ejected from the growth regions of our giant planets when the solar system was young. We'll visit that again in a minute. And finally, Fred Whipple, a distinguished astrophysicist, had hypothesized back in the early 50s that at the core of each cometary body, these beautiful tails of dust and gas that you see, many saw Hyakutake and Hale-Bopp, I think probably from here in Hawaii. Right at the core of that was a solid body which was comprised of this primitive material from the early disk, and that solid body had many ices in it, which were characteristic of the kinds of legacy materials that we might look at and learn more about the formation of that disk. So here was a kind of a picture. I haven't put the orbits in, but you get the picture of the planets as they were known in 1993. So what about today? 20 years have passed. We now have a Kuiper disk. Mike described that in detail in the last talk. It has 3 structures. These are dynamical structures: the scattered disk, the classical disk, and the extended disk. And most importantly, many members were detected, about many thousands actually, And the orbits for those told us that one special member of that group was the planet Pluto. And so Pluto became an ice dwarf. That's how it happened. And I think it was a proper decision. It's now ranked as one of the key things, bodies in the 3-2 mean motion resonance with the planet Neptune. In addition, the Oort cloud, the very concept of that changed dramatically. The ejection from the giant planets is still viable. However, it could be that some of those bodies, maybe up to 90% in some stellar systems, were captured from birth stars, sibling stars in the sun's birth cluster. They formed, these stars were being formed in the natal molecular cloud from which the sun and our planets formed. And they were ejecting material from their, other stars were ejecting material from their growth areas. And some of those could have been captured by our planetary system, by our star, and formed in part bodies in the Oort cloud population. But the most important change that's happened is that we no longer think that the giant planets formed where they now are. In fact, we know that they moved around. 2 new models have demonstrated this in particular detail by solving up to a dozen different standing problems on solar system history, evolution, and its structure. So this is actually a major change. The first model was called the Nice model, and so on. It's within this context we have to ask then, what about the Keck and its contributions? And finally, let me say that another thing that was changed was, for the first time, we actually had imaged 5 solid comet nuclei and many asteroids, and detected many of these primary volatiles, which was a particular role. These 2 things were particular roles to which Keck contributed dramatically. So this is what the solar system looks like today. And essentially, the Oort cloud has a diameter that's approximately 50,000 astronomical units. That is 50,000 times farther than the distance from the Earth to the Sun. So it's an enormous structure. All of the other material in solar systems in that little blue box there, if you expand that to the point where you can see the Kuiper belt, or Kuiper disk as it's sometimes called, Neptune being the outermost giant planet remaining, and expand that again, then you can see the inner planets in the asteroid belt. So we have a huge thing now that we didn't know existed in 1993. What made this all possible? This morning you heard from Ian McLean and Judy Cohen about the advent of these massively new instruments at Keck using massively parallel detector arrays. But the very advent of these large ground-based telescopes was absolutely foundational, no question. And Keck, as many people have emphasized, is the premier optical infrared observatory that made many of these discoveries happen and be possible. There were other contributors, of course, especially the Herschel Space Observatory at the Lagrange point beyond the moon, called L2, the launch and repeated servicing Hubble, and many spacecraft missions flown by NASA and other nations' space programs. But here we are, coming right back to Keck again, the premier optical infrared observatory. Keck 1, first light in 93, Keck 2, first light in 96. Okay, so let's look at just a few of the selected revolutionary milestones. I've actually emphasized things done first by NIRSPEC. NIRSPEC, as you heard from Ian McLean, is a high spectral resolving power infrared spectrometer equipped with, in a way that can measure the entire spectral range where most gases emit spectral lines in bodies such as planets and comets. So this is a really powerful instrumentation. So first thing that happened was when we commissioned the instrument in '99, we actually observed a comet on 3 of those nights, and this gave rise to the very first time that any comet had ever been measured with all the 10 primary volatiles, as we call them, measured simultaneously with water, the primary constituent. So at one glance, it became immediately obvious that a revolution had occurred and that we could now eliminate most sources of systematic error that often plague these kinds of measurements if they're done with instruments that are less capable. Well, a whole series of things then went on, and I've just highlighted a few in which the Deep Impact spacecraft actually flew by the comet Tempel 1 and directed a 300 kilogram copper projectile to impact the nucleus of that comet in 2005. And Keck was the only place that was able to demonstrate that the chemistry of the material ejected from the material that had been excavated was in fact different in its composition from the material that had been released in a normal way by the vaporization of water. So this confirmed indeed that the nature of the comet did change with depth, presumably because of surface processing. Later it observed with NIRSPEC a comet called Schwarzmann-Bachmann 3. This comet had actually split into many parts in 1995. And by examining two of those distinct fragments, we were able to look into the material that had once been stored deep within the interior of that cometary body. And so the surprise was that the material, gases being released from those two fragments, was indeed identical and the same. Other advances included looking recently at two carbon dioxide-rich comets, which have recently been demonstrated to be a major component in the planetary system, and so when these bodies impact on planets, they deliver a huge amount of CO2 and other gases as well. So since this, over this decade from 99 to 2013, if you'll pardon converting 14 years to 10, we've had 60 cometary papers published. Keck 1, meanwhile, has published a few with high-res for other fragment species. But it's definitely the instrument of choice for the community has been NIRSPEC. Okay, now moving on to the major planets, let's talk first about Mars. In 2003, the study of trace gases on Mars began at Keck. We had previously been using the infrared telescope facility owned by NASA on Mauna Kea and operated by the University of Hawaii for that purpose. But to our great surprise, initially we couldn't actually guide on Mars because it was too bright for the internal guider within the NIRSPEC instrument. Nevertheless, Keck was instrumental in detecting a new spectral band of carbon dioxide on Mars, a band which had never been seen by humans before in the laboratory or elsewhere, and which has later shown closes an important greenhouse window in the planet Venus. This is one reason why it's so hot, because it's got a very intense greenhouse gas there. So by 2009, largely through campaigns at Keck and here, we published this paper on methane. We then published a paper this year reporting the sensitive limits for 14 separate biomarker and geochemical gases on the planet of Mars. The issue here is, was Mars ever alive, or did it ever have active geochemistry, such as we see on the Earth, that could have produced trace gases such as the methane, ethane, propane, and so on, plus other nitriles and other kinds of gases. So this is something we're currently pursuing right now with Keck. And then the final thing I would say about NIRSPEC is that some of you may know that an upgrade has been proposed. So I'll call the current NIRSPEC 1 by comparison with NIRSPEC 2, which we hope will be funded. And this will, in fact, be the next revolution for high-resolution infrared spectroscopy at Keck. And we'll talk a bit about what that will do for the solar system. Now, I would be remiss by not referring back to the 3 AO talks this morning. You've seen and heard much from those folks. Winds on Uranus were detected in 2001 in the first AO planetary paper, and so on. NIRSPEC Laser Guide Star was instrumental in extending the quality of the AO images and improving that dramatically. And by now we have seen 93 separate refereed publications on planetary science using adaptive optics. And for those of you who aren't active scientists, a refereed paper is the gold standard in producing some paper of describing some science of relevance or discovery to the community. So this is a very important and very important metric, and we'll come back to the meaning of that in the case of asteroids in a moment. Just one example, OSIRIS was commissioned in 2005, and using it recently discovered the signature of salt on the Europa surface, and that is the first time we have any evidence that liquid water ocean may be in contact with the surface at the present time. This is a target for future searches for deep biospheres, because these ice worlds that exist in the outer solar system, of which Europa is one, it's a satellite around Jupiter, may in fact have incurred spontaneous or independent evolution of life below the surface of the ice mantle on the planets. And so this is a keen interest to explore that and search for that in the future. And finally, mention the Mossfire application, which will come up again in a few minutes. Okay, so the two key things were imaging and spectroscopy. Keck still is the premier facility with NIRSPEC for doing high dispersion infrared spectroscopy of gases and planets and comets and other bodies. In the imaging case, we talked about the importance of that for looking at cloud patterns on the outer planets. Here, for example, is Uranus seen with various clouds. From this, you can get the speed of the winds and so on. You'll notice that in this image particularly, the rings look fairly dim, and indeed they were not visible until they were discovered by infrared occultation on the Kuiper Airborne Observatory back in the 80s. But now we do it routinely from the ground using Keck. So let's take a look at these three cases that I've mentioned. Here's a better shot showing you the images of the various ring structures. This is Imke de Potter's work that was published a few years ago. And this is quite remarkable because you're seeing now the tilt of the ring pattern change as the planet moves through its orbit about the sun. You'll notice this is 2004, 2006, 2007. And so this gives one a way to look at the material in the rings from both the sunlit side and the anti-sunlit side and begin to understand what that's telling us about the nature of the material and so on. And may I say that this is one of the key features of a ground-based premier facility such as Keck. Namely, you can't always send a spacecraft to a planet and orbit the system for a decade. Cassini has now done that, but you can do it, you can make these studies from the ground if you have the right facilities. And so that's one of the reasons we're all here in this room, is to see some of those things that Keck has enabled and will continue to enable in the future with the help of the folks here. Now in the case of Europa, the interesting part here was that the idea was that, this is Mike Brown's work, and Kevin Hand, and what they found was that the salts were found on the trailing edge of Europa, but not on the leading edge so much. And the idea was that maybe the ejecta from the volcanoes on Io, another moon of Jupiter, which you saw in a beautiful image movie this morning, shown by Bruce McIntosh, but that material was actually it's rich in sulfur dioxide, and some of it comes around and smacks into the backside of the moon Europa, and then can react with things coming up from below and form these salts that are seen. So if that's true, it may mean that liquid water is also reaching the surface, or at least water vapor from the subsurface ocean, and give us some hope to actually sample that material and search for evidence for life there. Now the second test case that I will show is just the discovery of methane plumes on Mars. We don't expect methane on Mars. It's a carbon dioxide atmosphere, right? So like Earth, methane in our atmosphere is produced by biology, or the degradation of biological products. Similarly with ammonia, nitrous oxide, and so on. These are all biomarker gases on Earth. So one of the reasons that stimulated the search for methane on Mars was the idea that if it was there, it shouldn't be there unless it was being released now or very recently, because the photochemical lifetime of methane on Mars is only a few hundred years. So anything you see would have had to have been released during that time. So through ground-based spectroscopy, we actually succeeded in identifying plumes of methane that were released in northern summer on Mars in 2003. And with Keck, we discovered this and set new trace. This was done by IRTF and with Keck at about the same time. And we actually then went on and measured upper limits for 14 trace gases in a paper that was just published about 3 weeks ago, for those of you who have access to the literature. So this gave hope that there was, in fact, a region on Mars where we could detect these plumes, find out the depth from which they were being released, and the nature of the methane production. We must always, of course, as scientists, we have to be extremely careful not to be biased by our hopes. And so, because either mechanism could be at work, we need to search equally intensively for both solutions, biology versus geochemistry. And so we did that, and these gases that we now have published the first survey were done with the NIRSPEC instrument at Keck. We'll continue that work and apply adaptive optics in future with hopefully NIRSPEC 2 when it's approved and completed, so that we can actually map the whole planet and do, with an integral field unit, if it ever is built, funding available, we could then do that point by point on the Martian disk. Second thing is we want to look for the depth of methane release. We want to know whether this methane is coming from the surface layer. For example, on Earth, in the tundra regions, spring comes around and the tundra begins to become, the water becomes labile, meaning it moves around, becomes liquid near the surface. And microbial communities prosper under those conditions, and they produce a lot of methane on Earth. So if that something like that could happen on Mars, it seems unlikely, but if it did, we need to be certain that we could detect that and identify that. And so one way to do that is to look for the ratio of heavy to light hydrogen within the water that they would release. And the trick here is that we know that the water in the atmosphere of Mars is enriched in deuterium by a factor of 5 compared with Earth's oceans. Okay? So if any microbes are metabolizing that water, they would then release gases such as methane that were in fact enriched by this factor of 5 as well. On the other hand, suppose that the methane is coming from the deep subsurface below the permafrost region, then in fact, I never even saw one single card. 1 minute? Oh my goodness, okay. That was a minute ago. I'm in trouble. Okay, so what I'm going to do is skip a few slides. And you can look at these on the web, or you can ask me a question in the discussion period. I did intend to talk about the porosity of small bodies, and you've heard a little bit about that from Mike Brown. But there's a beautiful chart here which demonstrates that the big ones are not porous and the little ones are. Diversity of comets is dramatic. We'll talk about that later offline. And let me get to the Quo Vadis. Where's Keck going? Now, don't throw me off for this one because this is really important. And don't forget you started late. Okay. Okay, so we'll leave this up here, and maybe we'll just call for questions, and we can talk about the applications if need be.
Well, I'm confident. Thank you very much.
You're very welcome.